So we're still missing one bit of the proof. We are in the first part of this video lecture. We introduced product, sigma algebras, and sections, and stated a key lemma about sections, which was this lemma. And now we are in the middle of proving this lemma. We proved almost all of it. Well, almost all of it means we proved the first part. And now we're going to move to the second part, which will be actually simpler than the first, even though this is not what it would suggest. And how did we prove the first part? Well, what is the claim? Every set which is measurable with respect to the product sigma algebra, its sections by some fixed x, so a fixed x, its sections will be F2 measurable. And we did prove that, and we proved that by defining the sigma algebra, defining the family of subsets of the Cartesian product with this property. And then we showed that this family is a sigma algebra. And because it contains rectangles, it would also contain the sigma algebra generated by rectangles, which is the sigma algebra we want. And that's exactly what we're trying to prove. We're trying to prove that every set in this family has this property. And we are showing that the family of sets with these properties contains this family. So this we're showing exactly what we were supposed to show. And we have already done this homework of proving that this class G is indeed a sigma algebra. And what is remaining now is the second statement, which is if a function is measurable, then its sections are measurable. And of course, again, we can fix the first coordinate and prove that the resulting function will be measurable with respect to the second coordinate, because if we fix the second coordinate and consider now a function of the first coordinate, well, it will be f1 measurable by exactly the same argument, just replacing x by y. And how do we show that? Well, we want to show that for every set D in whatever is the sigma algebra of the target space, and here we are taking it to be Borel sets of R, but it could have been any space, really. So these are functions from omega 1 cross omega 2 to any third space, but we're taking it to be the real line. Well, how to show, again, that the function is measurable? Well, we show that for every measurable set D, the pre-image of that set, is in the sigma algebra of the domain of the source space, but the domain, it will be F2, because now we're talking about the function fx for x fixed. So it's a function only of y. So now we are taking the y pre-image of any Borel set D. We want to show that it's in F2. Well, how can we show that? Well, again, we show that taking sections behaves well with respect to other set operations, and in particular, the pre-image of a set D, by the section function is actually the same thing as taking the pre-image of that set D and taking the section of that set. Okay, we can try to see that. We can try to visualize that through a picture. We had fixed x, and then we had a function like this. This was our original function of both x and y. So this would be z would be a function of x and y. When we fix x, what we get is the function z equal fx of y. Here, now this x here is fixed. And what we are saying is, if we take a set D, a subset here of the real line, so this was omega 1, this was omega 2, can be any space. If we take a set D, then we can either consider all the pre-image of D in the surface, so it will be something, whatever is between two level curves. So let's erase this part. It will be whatever is between two level curves. So here, down here on the floor, it will be something like this. Okay, I'm making the picture for an interval. We can either take this set and then take the section by x, and this will give us here some set. Or we can look at the function that we had, take the section of the function, and then just look at the pre-image of that section, the pre-image of D by that section, and this will give us exactly the same intervals that we had. So this is what is being said here in this equality. And now that we have this equality, we can combine this with the first statement of the lemma. So the second statement is it is not simpler than the first statement, but its proof is simpler if we use the first statement, because now we have just seen that the section of a measurable set is measurable. And why is this a measurable set? Well, because we assumed that f is measurable. Okay. Well, we can write it like this. It's measurable having f1 product f2 as the source sigma algebra and having the Borel set as the target sigma algebra. So we can combine this with the previous part of the lemma to conclude, well, this is measurable, and because this is measurable, we can take a section, and the section will be measurable. The section will be in f2, and because of this identity here, what we just showed is that the pre-image by the section function of any Borel set D is in f2, and this is exactly what it means to say that fx from omega 2 to r is measurable. So this is the definition of being measurable, is that the pre-image of Borel sets are measurable. So this concludes this long third part of this first video lecture with the proof of this lemma.